Sure. Okay. Well, welcome to Cincy ML's Deep Reinforcement Learning talk by myself. I'm Akhil, computer vision engineer at PyTorch. Let's do it. So today I'm gonna cover a few reinforcement learning concepts, and for each concept, I'm gonna go through some theory for it and some code, and it's followed by demos. All right, so what is reinforcement learning? Any algorithm that learns by trial and error can be considered as a reinforcement learning algorithm. You would start off with random moves and see and eventually learn which moves led to winning versus losing. All right, so does reinforcement learning have any business value? Any practical applications? We'll see. There are a few. DeepMind is a Google-owned reinforcement learning company that reduced Google's data center cooling by 40%. Reinforcement learning can be used to teach robots to learn complex movements with high degrees of freedom. It can be used to place advertisements in the website. One could say we could even use it for trading. And if you're really crazy with reinforcement learning, you can create a company that would beat professional players in competitions. Actually, reinforcement learning is really used in niche applications within the companies. But you know what? I love reinforcement learning for completely different reasons. It's fun. I personally love playing games. And when I play games, I really think of how do I create an AI that would play this game like myself? It's like mimicking a human behavior in the games. And reinforcement learning is the closest thing that we have to artificial general intelligence. AGI, or artificial general intelligence, is this concept where AI gets so good that it beats humans at everything. And a general notion is that once AI gets to that point, it just keeps exponentially getting better, that it would quickly get better than even Einstein. This chart is from a good article by Wait But Why. You can check it out from the links here. The two companies that are working on reinforcement learning at the forefront of it are OpenAI and DeepMind, and they both are working on artificial general intelligence, is what they claim. So we know RL somewhat is synonymous to low-level general intelligence. That's why. And finally, RL is quite challenging. That's what I like about RL too. If you worked on deep learning applications, you would be familiar with these kind of graphs where the loss graph is smooth and clean, it asymptotes here. But try reinforcement learning. It's super hard to quantify if we're doing good or not. On the top right, we have a loss graph. It looks like the loss is increasing with these curves, and they're so noisy. By the way, these are the best, cleanest looking graphs I've seen. We will see a lot of messy ups and downs. Even though the loss is increasing, we see that the mean reward is increasing, which means the agent is doing good. So we don't know. It's not easy. It's not just only one graph wouldn't give us any information. That's why I like it. So let's get the basics out of the way. Every reinforcement learning problem has an environment or state. A state is a snapshot of an environment at some time point. And we have agents or an agent working, interacting with the environment. An agent would take an action. It could be one of, in this case, it could be one of up, down, left, and right. And for each action, the environment gives us some reward. Say in this case, you get a reward of +10 when you reach the green box and -10 if you reach the red box. And what's the objective of a reinforcement learning problem? It's just to maximize the rewards. Cool. So in reinforcement learning, each state on taking an action will transition to the next state, and it gives a reward. And taking another action will give us another state with some reward, and it goes on until some terminal state. And we can represent these states, actions, and the observed rewards within these sets of say state, action, reward tuples. And the whole sequence from start to finish is called an episode. Okay, this theory is nice and fun. We understand how a game works basically, but how would we code this? How do we write a code that would work with these transitions? Let's look at that. Let's look at it. The beauty of reinforcement learning, working with environments specifically, is that you don't have to create the whole game. All you have to do is interact with the game. And how would you interface with the game? It's using an interface, well, literally like an abstract class. Gym is a framework given by OpenAI that has a class called env, and you would override the methods to work with your environment. Here, the most important function is step. It takes an action, basically does some magic and gives you the next state and the reward observed. Every environment also has a reset, which restarts the game. Also render, which renders the current state. In some cases, it's just printing the state out. Okay, let's look at a similar environment to this. Here, P is the player. You take left, right, down, and up actions. They are encoded with integers, like say 0 is for left, 1 is for down, etc. If the player reaches plus, you would get a positive reward, and if you go minus, you would lose a game. And W is like a wall. You can't go there. Here, you see that the agent gets a -10 reward at the end. And the P slowly goes around and goes into the minus position. And that's why it got -10. And for each action, you see -1. Why would taking a random action give you -1? It's a way to tell the agent that you lose points for wasting time. Say you run around here and there and you get -1 every time. That's like losing points. So this will incentivize it to go to go in the fastest path. Okay, how much code do you think this piece of game will take? It's about 10 lines. You initialize the environment, reset it, and then take a random action and do env.step with that random action, and do it infinitely until it's done. Cool. Now, is this agent intelligent? We are basically taking random actions and and doing it enough times until we reach a certain state, right? We'll work on it and make it intelligent. Before I move to the next slide, I'll show you a demo of one of the interesting environments. That is Sokoban. Okay, want to make sure you guys can see this. So here's our agent, and there are a few blocks, and it wants to push the blocks to the right place. It took a right. Now I'm taking random actions. And you'll see the reward in the console here. It's too small, but there we go. The reward is 0, it took action 3, and now it went up, right, left, right, right. It's just taking random actions. But you know what? It's fascinating to see a program work on a game. It will never get close to winning this. It's a difficult game. I'll shut it down. Okay. How do we make this agent smart? So when we talk about smart agents, we can think of an agent as a function that takes in a state and returns an action, right? And can we replace this function with a neural network that takes in a state and gives an action? That's what we'll do. A state can be like a matrix or a tensor of some dimension. Here it's 4 by 4 by 4. You give it to a CNN or a linear network or any kind of network that you like. And the output would be a one hot vector or a softmax vector with a value it's like a probability distribution. Each row in the vector is like a value between 0 and 1, and the highest value will be the action that we'll take. Cool. It looks good. Let's put it in the network, in the code. So here I'm using PyTorch. This is the same code. I made a few modifications. One, I added a neural network. In PyTorch, neural networks are very easy to create, and in the domain of reinforcement learning, PyTorch is the easiest framework to work with. So that's why I picked PyTorch. Here we have about exactly 100 neurons, and it's a linear model, and output is 4 because we have 4 actions. Well, the next thing in the that's changed in the code is I commented out the random action part and replaced it with the neural network. We pass the state into the neural network in line 19, and in line 20 we get the action. Cool. Looks good, but is it still intelligent? Well, we didn't train it, so it will have randomized weights. So it's again similar to a random number generator, right? So how would we train this network? How would we make this smart? There's one way. Well, the goal has always been to maximize the rewards. So let's put our loss function as maximizing the reward, right? Take all the rewards, add them up, and that'll be our maximizing function, the function to maximize for. But neural networks like to minimize the objective function. So, okay, we'll multiply with -1 and then minimize it. It's the same as maximizing that. But this cannot be objective or a loss function because it's not derived from neural network weights, right? In neural networks, the loss function has to have a gradient, meaning we should be able to differentiate the loss value with respect to the weights. There's no gradient attached to this. Our neural network returns probabilities for each action, right? A number between 0 and 1 for each action. So we have those probabilities. Can we multiply the probabilities with the rewards and then do the same thing? Yeah, why not? If this is like we're weighting the reward with probabilities. Say we took an action that model says this is only 10% good action, but if we still take it, we are weighting the reward with only 10%. If an action is 90% good, if our model says that, and the reward is weighted with 90%, so it makes sense. And we can do a loss function like this. And my friends, this method is called policy gradients. A loose version of it, policy gradients can get much complicated. Let's look at the code for it. It's not crazy new. It's the same function. Here I am, first off, I'm sampling the actions from the outputs instead of taking the maximum value. This way, we will add some exploration to the to the episode. If we take the maximum value from the model every time, it would not learn because without exploring other actions, the model would not know which action is the best. That's that. And now we add the rewards and the probabilities to an array or a list. And at the end, we add them up, we multiply them up and multiply with -1, just like what we've seen in the previous slide. And that becomes our loss function. Boom. That's all. That's all you need to learn this simple environment. Let's look at the demo of this. This is the same code with some logging built into this. So I'm using the same loss. So I'll run it. And boom, we already see that our agent is playing a lot of games and it already outputted a video of it. So this is episode 0. The agent is actually stuck in this case. Well, in 3000 episode, we see that the agent already learned to go to the green box. It's taking not the fastest path, but it's going there. And 6000 episodes, yeah, looks like it learned. And how do we see if it's actually learning or not? Here in this graph, we see that the mean rewards for each episode slowly increases. It looks like a smooth curve. That's because I added smoothing. It looks like that. And we see that the loss decrease. So everything looks good. Wow. That's a simple one and it looks fun. So it's fascinating for me to watch the agent learn from these videos. By the way, I'm using weights and biases to visualize my training. I'll stop that. Okay. So what's the problem with this method? We can only learn once the whole episode is done, right? If you look at the loss function, it contains probabilities and rewards for the entire episode. What if the episode is like a million steps? We can't do that with such kind of environments. There's another method. What if we, instead of predicting like an action and then having this weird loss function, what if we predict the reward itself? For every action, there is there is a reward, right? For example, let's take stock investing. The actions you have are invest or don't invest, or you could call it sell, and the reward would be a stock up or stock down the next day. So if we predict tomorrow's reward, meaning up or down, then we know what action to take, right? So let's do that. Let's predict the reward. Let's take this date as example. Taking right will give me a reward of 10, and taking any other action will give me a reward of -1, just like before. So this is useful. Not so much. Take this state, for example. This state has -1 reward for every action. So which action would I take? There's no answer if I just predict the reward, right? But if I take action left, there is a long-term reward, right? Left, and then we have a path like down, down, and right, right. That'll give us a long-term higher reward. So how can we factor that in? Let's define what a long-term reward is. We call it return, and return is the reward plus a tiny bit of future rewards. So in mathematics, it will look like this. Reward equals current reward at time t plus gamma. Gamma is a small number between 0 and 1, let's say 0.9. And reward plus gamma times reward of next state plus gamma squared, which is much lower number, like 0.8 times the reward of that state. So as the time goes further in the future, the impact of that reward goes down. So this is analogous to a long-term reward, right? And we can simplify this equation to return equals reward plus gamma times return of the future of the next state. Cool. So now instead of predicting the next state's reward, let's predict the next state's return. So this will be what we will be predicting, and the label comes from the actual return reward that's observed, and gamma times the return of the next state. Let's look at this in focus mode. We are predicting return, and the label contains return of the next state. So can we do something like this, where we predict the return of the next state, and we predict the return of the current state, and use the next state prediction and the actual reward observed as the label. This is called bootstrapping. We are using the current model to generate the label as well as what we're predicting. It's not the entire label, as there's also a reward associated with it. let's look at it in a more graphical way so that we understand it better. Say there's a state and we predict the next return, which is again reward plus tiny bit of future reward. Now we take an action, so we select the action that has the largest return, and we step through the environment. The environment will give us the next state and a reward for it. The reward we see here is the same reward that's here as a label. And from the next state, we use the same neural network to predict the return of the next state. So that prediction goes here in the label. Now we have prediction and label. We can use mean squared error as our loss function. And booyah, there we go. For each step, we can learn, we can train the neural network. And this, my friends, is called Q learning. You'll see that Q, and I have Q and R. At this point, we can assume that Q and R are the same. Q, it's, more precisely, means state action value. We can get there later if you want to go. Okay, enough of the math jargon. Now let's look at the code. So here, I'm taking the maximum have a Q-valued action every 90% of the time, and every 10% of the time, I take a random action. Because once again, we want to explore different actions. If we just take the maximum value from the neural network, we are not going to learn. Reinforcement learning is more about how do we explore the environment and learn from it, as much as receiving maximizing the rewards. Well, I got the action. Now get to the labels part. I take a step in the environment. I get the next state in line 25. I take the next state and pass it through the model in line 28, and I'll get the next state's return. I use that as the label in 29. 0.9 is my gamma. According to our previous equation. And now our loss function would be a mean squared error. Okay, I hope this looks simple enough. And then we do our PyTorch learning here. Okay, let's look at another demo of this. Once again, it's the same code, taking actions, taking next state and loss and learning. I added some logging to it so that we can see weights and biases. Let's run this. Hello there. How is our model doing? I mean, I'm waiting for it to bring some more videos. Here you can see that the mean reward has slowly increased, and episode length is increasing. Okay, we got a new video. Let's see how the agent is doing. Okay, not learning as good. Well, here I'm showing you guys my previous runs with Q learning because of the interest of time. We will see that after certain episodes, it learns. Oh wait, maybe I'm showing you the wrong. Yeah, here. The mean rewards would slowly go high, indicating that it's learning, it's maximizing the rewards. The episode length goes high and then goes low because we are penalizing for wasting time. So the episode length will go down because it finds the fastest route to the green box. The reward, cumulative reward, keeps increasing because it gets plus 10 every time it reaches the green box. Cool. Let's get back to our presentation. All right. Okay. So in practice, there are a bunch of improvements to these two methods I've shown, both to policy gradients and Q-learning. I'm not going to discuss them, but you can go through them if you want to take a deeper look. Excuse me. So now we know that Q-learning and policy gradients are a way to teach an agent how to learn. What did bigger companies do with it? Here on the left, you're looking at Breakout. It's the classic reinforcement learning success game that DeepMind likes to show off. This was way back in 2000s. And DeepMind produced a paper where the Q-learning agent beats human players at a bunch of Atari games. You see the graph here on the right. There are like 30 games that are better than human. Well, the interesting part of this graph is actually at the low end. Take the last game here, Montezuma's Revenge. The agent learned nothing from it. The score is 0. Humans can easily play better than this. So why did Q-learning fail on this? If we take a look at the environment or the game itself, it's quite challenging. You see the GIF on the right. The player has to move around this maze type of environment and acquire that key. You know what? This looks so simple for in the video. I tried to play this game and I totally suck at it. It looks so simple than it is. It's super hard for me to play. I can't imagine why it was super difficult for the Q-learning. Well, in more technical terms, this game requires a lot of planning. There's no guidance from rewards, right? When do you get a reward in this game? When you acquire a key, and acquiring the key itself is quite challenging. Imagine taking random actions and going, and one of those random actions at some point will get you to that key. And do you think that's possible? It'll take like infinite amount of random actions to go there. And that is exactly why Q-learning failed, because Q-learning learns from random actions and then looks at which action is the best. Okay, so how do we solve this? The agents so far have no intrinsic motivation, right? There's no curiosity in a neural network. How does it know that I want to explore? It can't. Well, let's think about what curiosity is for a moment. when you want to know something and you don't know the answer, that is curiosity. Like there is an uncertainty about something, and you want to reduce that uncertainty. That is curiosity. Well, okay. How would we put this into our neural networks? Okay, let's think about it. There's a state, and you take an action. It'll give you the next state. So can we predict what the next state would be given an action and a state? Yeah, we can build a neural network that does exactly that. But sometimes we get a surprise, right? Taking an action would give us something different. And that difference between what's expected versus what's actually observed is a surprise, and that's something we can learn from. So can we consider that as curiosity? Yeah, why not? It's like you see an error in your prediction of next state, and there's a high uncertainty, and then you want to reduce that. So that's curiosity. Let's do it. Okay. I hope you guys are familiar with this diagram. This is the Q-learning diagram. We have Q-learning. It gives us a reward that is, when I say it, I mean the environment on taking an action gives us a reward. And this reward is given by the environment. We don't want to rely on the environment rewards. Why? Because of this. If I'm only relying on the extrinsic or the environment provided reward, I have to play like infinite random moves, and then I'll get to that point, right? Okay, so that's an extrinsic reward, and our intrinsic reward would come from the prediction of the next state. Cool. So I take the previous state or the current state and the current action and predict the next state. And the environment also gives us the next state. So I can use our predicted state and the actual state, next state, and do a mean square error, and it'll give us some intrinsic reward. I'm trying to edit this because this is supposed to be next state, st plus 1. Okay, so we got now our intrinsic reward from prediction of next state and extrinsic reward. We will combine these two and put it in our Q-learning loss function. Let's look at a demo. So a piece of advice, when you're working on reinforcement learning, don't pick a M1 MacBook, because most of the games or environments are built for Windows or x86 architecture, and ARM doesn't play well with these environments. So I wrote a code here with curiosity, and this plays for Super Mario Bros. I'm not able to run this here in my Mac machine. And by the way, this is an attempt at it. Reinforcement learning takes a lot of compute, and I don't have it. So this is an attempt, as I said. So here, this is one of my previous runs on a Windows machine. Okay, what do we see here? I will smooth it up. Okay. Um, we should be seeing a lot more of these graphs. Anyway, um, the Mario plays random moves and meets the enemy and dies. Oh, well. Uh, yeah, okay. Maybe it's here, maybe not. Yikes. Okay. Sorry about that. Oh, I got it. It's a different project. Here we go. Okay. Forward loss is the loss for predicting the next state. It's this loss, the intrinsic reward loss. We see that it takes a while. Oh, where'd it go? Here. It takes a while to go to the right values. Initially, the loss is super low. I don't know why, but then as the model learns about the environment, the loss goes high, and slowly goes down on asymptotes. And this is actually scratching the surface. The full graph would be long, and it'll take much longer for me. I just don't have to compute. Well, you could try and come up with better graphs. Oh, when I watch these videos, it's really fascinating. At one point, the Mario gets stuck at a pipe and doesn't know how to jump. And given more episodes, it learns how to jump, and we capture that in one of the graphs. X position, not X position, the X position. X position is the position of Mario in the X direction. So if it's moving forward, this graph would go high. If it dies, it would go sink to the bottom, like starts from zero. So we see that here it's blocked from this point to this point at a pipe or something, and it loses the game at some point. So there are a lot of insights that we can take, and not a single graph gives you the answer to what's going on. Yeah, and that is curiosity. There are other techniques to improve upon this for not random exploration, some sort of intelligent exploration of the world. Um, Random network distillation, episodic memory. You can take a look at these when you want to. So my final concept is model-based reinforcement learning. So now we built a neural network that learns how to play these environments. Can you ask these neural networks, well, what is your plan to win? You won't know the answer. Well, you can take the neural network, play it through like all the possible situations in the environment, and it'll give you an answer every time. Then that way you could call it a plan, but that's not helping you make a decision with your actions, right? Can you involve planning in taking an action? That's a whole idea behind model-based Let's take the most simplest game, tic-tac-toe, and you can place an X in 3 different positions from the root, and then you can take another decision, so it becomes a tree of decisions, and this is called game tree. Now when you build a whole game tree, you exactly know which path from the root to the leaf will give you the most reward and fast. That is, in this case, that is the action on the right. When you put an X there, it gives you a straight X, you win. Well, if you build out this tree, it's easy for you to win. For this game anyway. What if the game becomes large? Well, before we dive into that, let's look at a quick demo of one of the iterations of game tree. That is called Monte Carlo tree search. Let me demonstrate that trees always win. I'm gonna run this. Okay, this is small. Well, here X is X my player or not? Oh, okay, X is a random player here. O is the agent that builds the tree and finds the best path. So here, X, the random player, put it on the top right. Now the agent calculated probabilities for each action, and it's 50% on top right, 46 on that, etc. And for the middle position, it has 52. So it's 52% likely to win if the action is in the center, and that is where the O is placed. Random action placed next there, and now for bottom right, it's likely to win if it's on the bottom right by 64%. So O goes there, and random guy put it there. Now what's the highest percentage to win? What position gives us the most likely chance to win? That obviously it's top left, and that's what we see here. It's 1%, and that's where the O is placed. And this is another iteration where X is the smart player, and it wins. Okay, that's fun. Let's go back to this. The curse of dimensionality is real, and our computers go through it. When we had 9 positions, we would get a large tree that we can process with our computers. What if the board game has 19 by 19 positions? It's roughly like 3,000 power, 3,000 positions, which is basically infinite positions. Here's a visualization by DeepMind, laying out the whole tree, not the whole tree, one path, a few branches. It gets crazy, and we cannot compute that. So we want to have this planning, but we don't want to go exhaustive. So how can neural networks help with this scenario? One, do not take all the branches that are possible right? So narrow down the search space. Don't go too broad. We have two problems. One, going too broad, meaning taking looking at all the actions that you have. Two, too deep. Um, Too deep meaning take an action. You go level by level, right? In the tree. Going too deep is another problem. We don't want to go too deep or too broad. So for too broad situation, the model would select a few actions that are most likely to win, and we would only branch out with these actions, and we don't care about the rest of the actions. Okay. And for problem number two, going too deep, we could go to a certain depth and then ask the model to evaluate how good this state is without going too deep. Meaning, if I am in a certain state, am I more likely to win or lose? Is what we are trying to predict. Yeah, so let's look at the visualization of it. So we have the same tree. Now we eliminate the two broad thing. We only care about the actions that are good. In this case, the model could predict that taking this action in the middle might not be great, so we skip it. So now we have a smaller tree. And problem number two, too deep. Well, our model could say, okay, we want to only go 2 levels deep. That is root level and the child level. So here, for each child level, how good are we? How good are we? Are we gonna lose or not? So our neural network could predict that, and we eliminate the depth. So now we have a smaller tree to work with. And here, we know for sure that we will win here. So this is model-based planning. I did not write a code for it. You could. The paper is called Alpha Zero by DeepMind. Okay, so the problem with this is that you will need a perfect emulator to do this planning. What if you do not have access to the game itself to branch out, right? We have a few actions. We don't know what state will be if we take that action, or you don't know how to simulate those sequences. You can't do it. In that case, how would you do it? Quick answer, let a neural network learn it, meaning the state dynamics from one state to another is learned by the neural network. You take a state, an action, predict the next state, and you have the predicted state, given an action, predict the next state. Okay, so here comes mu0. It's again by DeepMind. How does it work? It has 3 neural networks for 3 different reasons. It does the same thing as game tree that you've seen before, cutting the branches down, that stuff, but entirely with neural networks and no emulator. Okay, so model H takes in a state and converts the state into some sort of embedded structure, like a vector or a tensor that embeds all the features of the state. This is mostly for reducing the dimensionality. Usually the states are highly dimensional, and we want to compress the meaning of that state into small tensor. So H does that. F is a neural network that takes in this encoded state and predicts P and V. What are P and V? P is a probability distribution over actions, meaning which action would likely give me a win. And V is the value of the state itself. Let's take a step back and see what those are. P is picking few actions, and V is the value of the state itself. Okay, so F neural network does that. Now G neural network does the next state prediction, which is take the previous state, take the action, now predict the next state. Next state here is the encoded state, and it also predicts a reward. So now we have a learned emulator, and Google DeepMind used this technique to learn chess, Go, Shogi. Shogi is Chinese chess, also Atari games. There are a few other techniques, like Dreamer V2, GameGAN, inverse RL, on offline RL. These are concepts that you can take a look after. And that concludes my talk. Here I have a few resources, key papers, and a Discord that you could join. A lot of people support each other there. Some other notes on Reddit. Thank you.
Hey, Akhil.
Hey.
I was going to say, hey, thank you very much for this very engaging and interesting discussion. I was going to open up to questions on the floor. I'm sorry I cut you off there.
Sure.
Yeah.
I'm waiting for questions.
Yeah. Thanks for the talk. Very interesting discussions. I was wondering, like, can you share the presentation? Or
sure. I will share the presentation as well as the code in the meetup discussion description.
Cool. All right.
Or in the comments.
And I can put that into the LinkedIn event as well.
Sure.
Thank you.
Any other questions, guys?
Every time I thought of a question, it ended up being a part of your presentation. So I was
really
one of the things I was first thinking or was wondering was if you had tried it on anything a little bit more difficult than just touching the green blocks. Like, have you run it on that original game that you did with the blocks, moving the blocks from onto the specific the one that you had on the pop out into the specific spots.
Right. Sakoban, right? This is such a difficult game. No, but I would love to, and I would encourage others to take a jab at it. No, in short, no. My agent tries random actions and gets itself stuck. Like all the blocks go to the corners and it doesn't know what to do, and it restarts. So it's like, again, it involves a lot of planning. Yeah, so I need some bigger guns for this game.
Yeah, that's really interesting. That something that looks so simple
Right.
can be quite complex.
Right.
And that was my other question, was about building in some sort of memory, like we do with long short-term memory, those types of equations that take into account past.
Sure. What you're talking about is called Markov decision, or Markov thing. That is to take a next action. All you need is current state, is what Markov decision says. But you could scrap that and take previous actions into account, meaning take the past few states, sorry, and that will predict you the next. And you can also try recurrent neural networks, which for each state transition, you would build memory in a short-term weight tensor. That usually helps. And there's another concept called episodic memory that one can explore and see how that works.
It's all really fascinating. I've always been interested in trying reinforcement learning, but I've never had the bandwidth or the or just this kind of helpful overview to see actually how approachable it is. I'm quite surprised that it's this approachable.
It is. And there are a lot of really supportive community for reinforcement learning. The Discord, for example, is really active, and people ask a lot of questions every time. And if you have a doubt or if you're stuck, people really help you out.
So this is the last question I have, but all of the examples here are video games, but you did have a stock trading example in the beginning where the reward was, stock goes up or goes down. Have you done anything outside of this, outside of games in I mean, not necessarily stocks, right? Because I mean, I don't even think humans can really do stocks well, but but have you ever tried? I know you do computer vision. Have you tried to apply it to that or anything like that to improve efficiency?
Excuse me. No, I haven't, but I have a few colleagues who have tried reinforcement learning for some of their very niche problems, where one problem was a weird graph search, where which node in a matrix do you want to go first, and how do you explore? I can't explain it, but there are a few business applications. I personally haven't tried anything besides the games.
It's always a challenge, but yeah, it's very interesting. Does anyone else have some questions?
By the way, DeepMind has a movie on YouTube called AlphaGo. I highly recommend everyone watch it. It's super fascinating documentary of their AI system. I have a link for this in the sources mentioned here. If anyone has any questions, please go ahead.
Right. Well, I think that may be it. Do you have a Twitter handle or anything that you could share with us in case people want to reach out to you?
Sure. I left my LinkedIn link. You can always find more links at my website. I don't use Twitter that much, but LinkedIn should be a good place to reach.
Perfect. Yeah, I honestly I have a couple of Twitter accounts that are run by bots, but I don't personally use it. All right, great. Well, thank you so much. I have recorded this talk, as everyone saw when you came into the presentation. So we have a new YouTube channel, and I will try to post this to that as soon as I can. Thank you so much for your time. I appreciate the talk. It was, again, really engaging, and thank you everyone for showing up.
Thank you all. Bye-bye.
Thank you.
Bye-bye.